Okay, welcome to our next video. So in this one we're continuing with the final exam from fall of 2024. This is our problem number 3, part A. Evaluate the integral. Okay, and we have the integral of x times e to the 2x dx. So looking at this carefully, we should notice that this can appear to be a integration by parts problem. Okay, remember with integration by parts, we have integral, if we call it, let's say u dv, this will equal u times v minus the integral of v du. Now the main question is which of these is going to be our u and which is going to be our dv, right? Because this is what we're starting with. We have to make a determination of which one is which. So I typically tell my students that our u is going to be something that we could easily take the derivative of. And by taking the derivative, the function, the expression ends up becoming a simpler degree expression as a result. The dv is something we could easily integrate repeatedly. Okay, that's something that we just have to pay attention to, because dv, when you integrate, turns to v, and then the u, when you integrate it, turns to du. Okay, so I'll set this up on the side here. I'm going to say my u is x and my dv is e to the 2x dx. Okay, so if u is x, then du will be 1 dx, or just, if you want to say dx directly, you could say that. If I have dv equal to e to the 2x dx, then integrating this will give me v equals, now we have an e to the 2x. Keep in mind, every time you differentiate e to the 2x, you're going to end up multiplying by 2, right, which is the derivative of 2x. To offset that, we're going to multiply by a half here, right, because we're integrating. And so just to picture, did we do this correctly? Take the derivative, e to the 2x is e to the 2x. Then we'd have to multiply by 2, right, for the derivative of 2x. Multiply by 1/2, and we're at our e to the 2x dx. Okay, so it looks like we're good. Now let's just plug into our formula piece, right, which will be this portion. So we have uv, so x times 1/2 e to the 2x, or I can just merge it together and say this is 1/2 x e to the 2x, okay, minus the integral of v du, so 1/2 e to the 2x dx. Okay, and now we could integrate this portion. So just like we integrated here and we went from an e to the 2x to a 1/2 e to the 2x, we'll have to account for another version of this. So another 1/2 multiplied to this will give us 1/4. So 1/2 x e to the 2x minus a half times this half would be 1/4 e to the 2x plus c. And so that would be our final answer. If you have any hesitations about this, take its derivative, right? Take its derivative and then you would see that you should end up with the original integrand here, x e to the 2x. Alright, let's move on to our next problem. Okay, so another integral that is not very easily evaluated. So this square root of 4 minus x squared, this should remind us of our integration by trig substitution. Okay, so and now looking at the model for it, we have a constant minus variable. Okay, you could think of this as a constant squared minus a variable squared. Okay, and this invites, so if we're thinking of it like this, this invites us to say the triangle. Okay, and every time you do one of these trig substitutions, integration with trig substitution, picture the triangle for it. Okay, so that square root will end up somewhere in the triangle. For our particular triangle, this will be the bottom leg. Okay, and the 4 is our 2 squared. Okay, so 2 would be our hypotenuse. And then the x squared, so we know that x would be our other leg. Okay, this is just one of those forms that I tried to memorize. Okay, obviously we have 2 other forms, but this is probably going to be the one that we're going to be using this time. So if this is our form, then we have to figure out what are we going to substitute, right? So what's going to be the substitution? So that means that this is going to be the sign substitution, right? We would say the sine of theta would be opposite over a hypotenuse. Okay, so sine, in this case, x over 2. So in other words, if I multiply both sides by 2, I'll have x equals 2 sine theta. And then if I have a dx, just take its derivative. Derivative of sine is cosine, so 2 cosine theta d theta. Okay, so let's get started. Don't be afraid of the trig substitutions. Some of them have multiple steps. So if you see you're getting pretty lengthy in terms of steps, no fear, because sometimes that's what ends up happening, right? Okay, so let's get started. We have our integral, square root, 4 minus the x squared. Now, if we have x is 2 sine theta, x squared, so picture squaring this, 2 sine theta times 2 sine theta will be 4 sine squared theta. And then dx, this is a common mistake people make. They forget about dx, they just copy it down, but dx is right here, 2 cosine theta d theta. Some people just totally forget about it. And that's probably one of the #1 mistakes. Okay, so don't forget to put that in. So we have times 2 cosine theta d theta. Okay, so now we're going to try to maneuver a little bit. We're going to inside the square root, I'm going to set aside the 4. So I have left 1 minus sine squared, which we all know it turns into cosine squared theta. Square root of 4 cosine squared, we could easily take the square root, it's a perfect square, turns into 2 cosine theta. And now we could multiply the 2 and the 2, the cosine with the cosine. So we have 4 cosine squared. What I'll go ahead and do is I'll pull the 4 outside. Right, it's a coefficient. So I'll have 4 cosine squared theta d theta. Now we cannot integrate that, so we're going to have to use trig identity to replace the cosine squared. A very common trig identity for cosine squared will be our 1 plus cosine of 2 theta all over 2 d theta. Okay, we can cross cancel between the 4 and the 2. Right, goes twice, so we have a 2. So 2 integral 1 plus cosine of 2 theta d theta. Okay, and now we can integrate. So when we integrate this, we have R1 will just become our variable. Right, so theta in this case. And then integral of cosine is sine. So sine of 2 theta. And then we have to figure when we do a derivative of sine of 2 theta, we're going to end up multiplying by 2. This one doesn't have the 2, so what must have happened? Must have been multiplied by a half. Okay, so we have 1/2 sine of 2 theta plus c. Now you don't end here. Another common mistake people make, they do the integration and then they stop. Remember, for trig substitution integrations, you're starting with x, right? You're starting with a variable, right? Most commonly x. You must make sure to end with that same variable. Okay, so if you start with x, you got to end with x. Okay, the trig part is the intermediary, right? That's all the in between, the middleman. Okay. To make this a little simpler, I'm going to distribute into the brackets here the 2. So I have 2 theta plus, and then the 2 will cancel the 1/2. So just sine 2 theta plus c. Okay, so now another thing, I'm trying to convert this back to my original variable, the x's, right? I want to begin with x, end with x. Now in our triangle, we don't have a 2 theta, we have regular theta. So we're going to use another trig identity. Okay, so that's going to replace the sine of 2 theta, and so we have the trig identity. Sine of 2 theta is equal to 2 times the sine of theta cosine of theta. Okay, and now that's what we'll use Okay, so we could go back to our triangle, and now we could start plugging away. Okay, so we have sine of theta is x over 2. If I'm just trying to get theta by itself, which is part of my answer here, I could do an inverse sine to both sides. So I have inverse sine both sides will give me theta. Right, theta equals inverse sine of sine is theta, and then inverse sine of this side. So theta will equal inverse sine of x over 2. Okay, so I'll just write this up here. So that means I have 2 times the inverse sine of x over 2 plus 2 times sine theta cosine theta. So two times, okay, sine theta, we have that already, that's x over 2. And then cosine theta, that's our adjacent over hypotenuse, so that's the square root of 4 minus x squared over 2. And don't forget the plus c. Okay, we could clean that up a little bit, so we'll just say this is 2 inverse sine of x over 2 plus, just cancel maybe this 2 and this 2. So we'll have x times the square root of 4 minus x squared over 2 plus c. Okay, let's take a look at our next problem. Use known series to write down the first 3 non-zero terms in the Maclaurin series, which is our Taylor series about a equals 0, for the function f of x equals x cubed e to the negative x squared divided by 1 plus x squared. Okay, so the trick to all this is to try to remember what some of these common Maclaurin series look like, right? And then another issue is how this thing is written. So if there's another way to rewrite it, I would say let's try that. We have x cubed e to the negative x squared, and it's all divided by 1 plus x squared. So that's one way we could rewrite it. And then another way, after looking at it a little bit further, is we have x cubed, and then we have times e to the negative x squared. And we could rewrite this and say this is times 1 over 1 plus x squared. This last version is the one that's going to really help me a lot, because I can try to figure out something for this one, and I could try to figure out something for this one, like meaning something in terms of like a Maclaurin. X cubed, there's really nothing for it. That's just going to act as kind of like a, like a term that we're going to distribute into these. Okay, so let's revisit and try to remember some common Maclaurin series. Okay, the e to the negative x squared, I'm going to get influenced by e to the x. Okay, so e to the x, remember, would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... and it'll just keep going. It'll be something like x to the n over n factorial. Okay, so then what does that mean for us? Well, instead of e to the x, we have e to the negative x squared so it's basically like replacing x with negative x squared, right? And same thing in the formula. We'll have 1. Okay, now replace x with negative x squared, so we have minus x squared. And then plus, replace again x with negative x squared. We square it, we get x to the 4th. Okay, same thing, negative x squared being cubed, that'll be a negative x to the 6th. And then x to the 8th over 4 factorial. And then obviously this will keep going. You'll have a minus here, and then a plus, it'll just keep alternating. Okay, as far as our 1 over 1 plus x squared, this reminds me of the Maclaurin series for this one. Right, this was like our old geometric series where common ratio is x, first term is 1. Okay, so this gives us 1 plus x squared plus x cubed plus x to the 4th Okay, so then that will remind us of if we have 1 over 1 plus x squared, okay, well now you're going to be looking at replacing x with an x squared. The only thing you might want to picture is, try picturing this as something like that, where you have 1 minus negative x squared. Right, so then that's going to change. So now you can just make that direct swap. Okay, so then you'll have 1 and then minus x squared. And then when you square the negative x squared, it'll be plus x to the 4th. And now negative x squared cubed, that'll be a negative x to the 6th. And then plus x to the 8th. And then minus ... and then these signs will alternate and you see the pattern. Okay. So let's take a look and keep going. So now we're going to substitute in for our expressions here. So we know what e to negative x squared will look like. Okay, it'll be this expression. We know the 1 over 1 plus x squared will look like this expression. And then we have the x cubed in front. Okay, I'm just going to erase this for a second because I need the space. So I have f of x. Okay, we'll have our x cubed. Okay, and now let's put in our e to the negative x squared. So that's our 1 minus x squared plus x to the 4th over 2 factorial. And we could already go ahead and evaluate 2 factorial as 2. Okay, you don't want to go too deep into this because you only want to write down the first 3 non-zero terms. Okay, so we'll do that. And then our 1 over 1 plus x squared, so we know those. That'll be 1 minus x squared plus x to the 4th. Okay, so the bulk you could really focus on are the 2 trinomials, if you will. Okay, so kind of keep the x cubed hanging out for now. So now distribute the 1 to everything. So we have 1 minus x squared plus x to the 4th. Okay, now switch gears to the negative x squared. Negative x squared times 1 is negative x squared. Negative x squared times negative x squared is a positive x to the 4th. And negative x squared times x to the 4th will be a negative x to the 6th. Okay, and then now let's switch gears to the x to the 4th over 2. X to the 4th over 2 times 1 is x to the 4th over 2. X to the 4th over 2 times negative x squared will be a negative x to the 6th over 2. And then x to the 4th over 2 times x to the 4th will be a plus x to the 8th over 2. Okay, look to combine like terms. Let's see what we have. We have x to the 3rd. We have the 1. Minus x squared, and another minus x squared is a minus 2x squared. And then we have x to the 4ths. We have x to the 4th plus x to the 4th plus a half x to the 4th. So that's 1, 2, 2.5. So 5 over 2. So plus 5 over 2 x to the 4th. we have x to the sixths. We have a minus x to the sixth and a minus 1/2 x to the sixth. Minus 1/2, so minus 3/2 x to the sixth. And then we have a 1/2 x to the eighth. Okay, and so now from here, what we can do is distribute the x cubed. What I'm going to do is just write it up in this blank space. I kind of ran out of room here. My apologies. So this will turn into, let me write this in green. If I distribute the x cubed, that'll turn into x cubed minus 2x to the fifth plus 5/2 x to the seventh minus 3/2 x to the ninth and then plus 1/2 x to the 11th. Of course, all you're really focusing on, they say the first three non-zero terms, so you'll do that, right? Those are your first three non-zero terms. Okay. All right, let's take a look at, there's a follow-up to this one. Use the series found in part A to determine the fifth derivative of the function at 0. And they tell us, do not attempt to differentiate f of x 5 times. Okay. So the way this is going to work, we're going to be focusing in on the fifth derivative, as they say, right? They don't want us to differentiate f of x 5 times, but they want us to focus in on the fifth derivative of x. So remember, when we do the Maclaurin series, the Taylor series, right, what these terms represent. So if it's the fifth derivative, right, the fifth derivative term in a typical Maclaurin series, right, this is going to be the term that has the fifth derivative, and you'll have the 5 factorial in a denominator. Okay, what does this mean? So this really narrows it down to our term with our fifth degree. Right, the fifth degree term is going to narrow it down and give us what the fifth derivative is, basically. Okay, well, how do we set this up? So we know that we're doing this, right? And so if we look at our term with our fifth degree in it, right, that's the negative 2x to the fifth. Well, the coefficient, right, that's going to be all what this is. Right, this fifth derivative at 0, right, that's going to be all part of what gives us this negative 2. Okay, so if we set that up like that, okay, and now we just kind of rearrange this, multiply by 5 factorial, both sides. Okay, that'll allow us to cancel. And so now we have our fifth derivative, I should say, at 0 equal to -2 times 5 factorial. Okay, so basically we're doing -2 times 5 times 4 times 3 times 2 times 1. So 5 factorial, 20 times 3, 60, 120. So -2 times 120. So we have -240. Okay, so I'm just going to erase that. So our fifth derivative of f of x at x equals 0 would be -240. Okay, and so that's the end of our second part. I hope this is helping those of you that are watching this. And we will continue with the next part. Okay, have a great day, have a great night. We'll see you soon.